Okay, welcome back to part 2 of the ICOM IC-725 that's been really badly damaged. Quick recap about part 1. Obviously, we took a look at the radio, we took it apart, and we basically assessed the damage. And you can see, it's obviously landed on its VFO and the rotary encoder, and basically it's smashed the board. So the tracks were broken. So basically what I've done, there was 2 main cracks. There's one that comes up here and then heads along up to here and then stops. And then there's another one that started from this section here. This is the cutout for the rotary encoder. And then it's come along and it's travelled all the way up. It's travelling up here. So if we want to zoom in, I've obviously patched this up. This doesn't look very pretty, by the way. So basically, there's actually a bit of wire in there, but it doesn't matter. This section's not doing anything. It's just a bit of ground playing. There's a bit of wire here because there's this track that comes along there. I don't know if you can see that was damaged. And then the crack came across, and this is where it gets a bit tedious because we've got our, the LCD driver IC, this little NEC bad boy. It's come across here. So what I've had to do is attach wires, fine wires, at, alternate intervals. So what I've done a bare wire, then one with a jacket, a bare, and one with a jacket, just to try and keep them separated. I've looked under some magnification, and I've done a few tests on it. So it's electrically sound, and but it just looks bloody awful. I mean, it's not something that if I was doing a repair I could do for a customer, because but yeah, the radio would be a write-off. But in the interest of making this video, that's what we've done. And if we look over the other side, yeah, the crack came along here. And basically what I've done, I've just put wires from each, where where each component comes through the board, and just soldered on and tagged on a fine wire. Now, if you do this, I just always double check. I'll double, triple check this, and I messed it up. So easy to, it's so easy to, miss some, tie one onto the wrong thing, and then you don't know what's going to happen. It could cause damage, or things don't work properly. But that's what we've done. And obviously I've used this fine linking wire. This is the wire I use for prototyping. So, okay, let's zoom out. I've also had a go at the front panel. It's still, I don't know if you can see that, it's still got the thing's got a bit of a bend in it there. It's not too bad, but it must have had a hell of a whack, this thing. I mean, the radios weigh, what are they, they're just shy of 5 kilos, which is, I guess that's just over 10 pounds in weight in Imperial. And this section here was really badly domed in. A lot of it was misshapen. I've managed to do it. I've got a little panel beater set. It's just a cheap one I bought some time ago for another project, but with a block and slight tapping, I've managed to get it to come back. Now I think this is going to be okay. Yeah, but it's still a little bit misshapen, but yeah. Well, okay. Well, we're going to run with this. I want to see if we can get the thing up and working. Okay, if we go back to the board, there's another thing I just want to point out. Have you noticed this? Now, obviously, because the LCD's, it's broken, what tends to happen, they tend to bleed. I think that's probably the right terminology. And anybody who's had a digital watch or something that's cracked the face, you can over time see them bleed, so that they all become black. And it's exactly the same, I imagine, would happen with this. So, but you never know, we might get something here. That's what we're trying for. And it would help if I could see something here, because ultimately I want to look at the serial data that's coming to this, and see if we can intercept it and possibly build a new display for it, probably using an OLED display, and we can program another microcontroller to do it. But okay, well, oh yeah, just before we move along, I'm just going to have a quick look at this mechanical. If you can zoom in, if I can get a bit of light in there, you might just be able to see. So as I turn it, can you see that? There's actually a little wiper coming across. So, basically how this thing works is, obviously it's just a lot of the mechanical ones, they're just two switches that go independently as you turn them, and obviously whichever one leads, you can actually, in the programming, you can get it to, you can use it, do it with the flip-flop as well. You can work out which direction, so you can have your count, which is just giving you a square wave, and then it flips. So I'm a bit worried, because these have to be, they have to be quite accurate in order to work. It has to be right, otherwise it won't work. So just hang on, I'll see if I can. Normally what you do, you put 5 volts on something and some pull down resistors, or vice versa. So let me just see if I can put it on the scope, and we'll see what we're getting out of it. Okay, so hopefully you can see this. Obviously we've got the rotary encoder here. What we'll do, we'll try and give it a little test. The way this is a mechanical rotary encoder, and the way these things work, there is a bit of precision in here, obviously, on which line fires. Obviously, what I'm doing, I'm putting 5 volts on. If we look here, just ignore the battery. I'm just using the leg off it, because it fits conveniently into this little Molex connector here. I've got 5 volts coming off here. I've got my scope. Hang on, I'm getting in a bit of a mess here. Hang on. Okay. So basically, what I'm doing is on this, I'm giving it 5 volts at the center point there. So what I'm going to do is put the scope probe on, which I've also got common to the negative on the power supply, and we'll give it a turn. So let's see if we can. What I'm going to do, let's bring it up to the scope. We're just on. It's just DC coupled at the moment. I think it's about 1 volt or so per division, somewhere around there. So okay, so if I'm going on the outside. Okay, we can see some noise. I'm turning it now. Okay, so we can see square waves. They're a bit noisy on the top, but that's just a byproduct of some of these rotators. You can clean that up with they generally use Schmidt triggers to clean that up. But that's one side. Let's see what it's doing on the other. Yeah, we're getting the same. So I'd say that's okay. I mean, the way to really test it is put 2 probes on, and then you can actually, but you can look at the correlation between the, one pulse and the other. So I don't know how many pulses. There's normally, these, when we look at these things, rotary encoders, the resolution is how many pulses per revolution. Obviously there's no detents on this, which a lot of them have, but that's feeling quite smooth. It doesn't appear buckled, which is another thing, because it seems to be made of, the shaft's aluminium. It's had a hell of a knock, but yeah, I think we've just been lucky. Okay, well, I'm going to put the radio semi back together, and let's apply some power to it, and we'll see what we've got. Okay, so I've got it together. I've connected some power. I've not switched it on it, so I don't know what's going to happen. You are going to see exactly what I'm going to see. I don't know. The fuse holder's broken. I've bypassed it. There is a fuse there. However, this is a current limiting power supply, so I'm not too worried about that. So what I shall do is let's try it on its side. Now, there's one thing with these. They're very easy to connect into, to connect the cables into the wrong sockets, because there's a lot of them are the same. And obviously on some equipment, they make the connector slightly different, and so that it's difficult to do. But on these, it's just obviously the era of the radio, and, if you're not sure, you take photographs like I didn't. But I had got the film, so I went back and, obviously this footage. So I went back and I could find where everything went. But yeah, good safety tip. Take a good detailed photo, just with your phone or something. Yeah, it pays absolute dividends. Okay, so let's see what we've got. We're in the off. We're in the off position. We're not in transmit mode. Set the limiters on 2 amps. That should be enough to drive it for receive. So let's put some juicy Lucy on it. Okay, we've got juice. It's taking power. 2 milliamps. Gone down to, that's probably just a capacitor. So everything's turned down. Everything's connected, so there's a speaker there. So let's see what we get. Woohoo! Nothing on the display. Oh, I can hear something. We got absolutely nothing there. Yeah, it's probably too far gone. There's bits of this thing absolutely everywhere. If you see that, look, it's bits, literally bits of it everywhere. So it's the outer is the RF gain, so RF power. So I'll turn that down. Let's get rid of that. Let's come back to the Z radio. Let's see what happens when we put it into transmit mode. It's probably going to collapse the power supply. But if we look on there, let's just see if I can slide this over gently. Ooh. Yeah, she's pulling 740 milliamps, which I haven't checked the spec, but I imagine that's pretty good. Actually, some of the radios I've built pull nearly double that on receive, but it's me, it's designed. Oh, I can see something on this screen. Hang on, let's stand by. Oh, let's just try transmit first. Nah. The power supply won't allow it. I was hoping to do it so that it'll idle, but it's probably just too much for it. Okay, well, let's just turn it off a second. shall do, let's move this thing over, have a different angle. I saw something on that display, and maybe, just maybe, let's see what we've got. Yeah, to prop it up with here. Here we go. So we put that underneath it, and we can see if we can see anything on the screen. Okay, I can kind of see something there. I wonder if it happens if we try and tune it. Okay, so let's put an antenna on it. Okay, so I've done a bit more investigation. So, well, let's just run through it. Obviously, we've got AF gain, which seems to be working. That should be the squelch, which seems to be doing its thing. We pressed that before. It went into one, obviously, because we're on current limiting, but that's to transmit. This should be noise blanker. It doesn't seem to be making much difference. It's probably a gated noise blanker, which it's not, you know, it's what it's sampling isn't the right condition. Attenuator. And you can see so that seems to be working. We've got preamp. Seems to be coming up slightly. Obviously, then the meter's working, which I was worried about the action. So if that had shock, it could knock it off its axes rather. Let's preamp. So there is something there. The AGC's doing something. I don't know what that's doing, whether it's a fast attack or slow AGC or slow attack, I don't know, but it seems to be doing something. So I'd say the radio's pretty good, and we can test the. Where's my pencil? It's gone into the vortex. Okay, so we go on to here. We've got upper sideband, lower sideband, carrier wave narrow. That'll be AM, FM. Okay, and on this side we have. Now I think I've just had a quick look at the manual. I think that this is how it works. So we've got, if you press the band button, it skips through. When you turn the VFO, it skips through the bands. But it just keeps doing it. It's a shame it didn't stop, you know, when it gets to the bottom band. So obviously it goes to the bottom and then goes back to the top band again. And we could at least work out where we were. Okay, and then we've got, once you've selected your band, to get around the band, you can press the megahertz, which will make it move in megahertz. Then you press the kilohertz, which makes it move in kilohertz, so it's tunable. We've got the RIT, R-I-T. I did test that before, it was working. And we've got VFO. So that must be A, one's B. And it's obviously changing the profile as well, which is correct. Split, I'm not going to play with it. I think this is okay. And in fact, you know, I'm quite confident it is. But I need to, in order to start interrogating it, we need to know what frequency it's on. And honestly, it's like ships lost in the night if you try and put a signal generator on it and try and find it, or vice versa. Yeah, try and get the radio to find the signal generator. But yeah, that's not going to happen. So what I've done, I've ordered a CIV cable from eBay of a chap Technofix. I've had stuff off them before. I bought a load of ceramic filters off him for doing some experimental work, and they were very good. So hopefully the cable's good too. I'm sure it will be. So we can't really do much more. We know it's receiving. What would be a good idea is actually have a look in the transmitter. I could technically connect it up and start it transmitting, and that'll tell me what frequency I'm on, but yeah, it's a bit hit and miss. But let's have a look into the let's get a transmitter apart, let's have a look. I just see the condition of it. So but I think we've got a good radio here, and I think we can make something of this. Okay, so this is our PA RF power output section. We've obviously, that's the RF amplifier, and we've got our low pass filter array here. And looking down here, it looks like I don't know if you can see that, there's a little neon down here. That's static, electrostatic arrest, lightning protection, whatever you want to call it. But it's actually looking in really good condition. Normally if they've had a lot of use, you start to see sections of the board starting to darken, and that's through prolonged use or bad SWR, high power, and it starts to degrade. But this all looks really clean. It looks brand new. So this radio clearly has not had a hard life. Somebody's looked after it, or it's simply just not had a lot of use, full stop. Okay, so if we have a look at the PA, we'll just go have a quick run through it. So if I can zoom in. Okay, let's bring it a bit further forward. Okay, so this is using Mitsubishi. It's the Mitsubishi suite of HF RF transistors. Well, I say HF. So at the beginning, we've got RF coming in. That's our signal we want to amplify, comes in here. We've got a pre-driver, which is it's a 2SC1971, which is quite odd, really, because I believe that's a VHF transistor. It obviously works fine on HF. Yeah, that's normally a VHF transistor. Then obviously we're coming through, we've got a little transformer here, which is basically a balun. So we single-ended, and then obviously we balances, and then we've got a balanced amplifier. We're using 2SC3133s. I think these are about a 15, 18 watt transistor. You get in Citizen band equipment, I think they used to use a 2SC1969. I think these are a little bit more juicy. I think you do see these in some CB equipment, but it'll be old CB equipment. But yeah, we've got a balanced amplifier. This is the driver stage, and what we've got here on that little bad boy there is a little diode. Basically what that's for is to do the bias tracking, because these are being bipolar. There's a current setting that you have to set the bias, so it keeps the stage nice and linear. If it's quite critical, I imagine it's one of these you have to adjust, and there's normally a couple of tabs or something you can open. You can put an amp meter on and you set how many milliamps it is. But the idea of this is that you normally have a driver transistor, and what happens is, because of the characteristics of the gain characteristic, and the curves change as they get warmer, as they start to heat up. And the idea of the diode is that's doing exactly the same. And what it'll do, it actually tracks the bias. Well, that's the idea. But that's basically it. And then obviously we go into another transformer here. which I'm not quite sure. I mean, it's just a balance transformer. It may be doing some impedance changing, transformation. We've come a bit further down. We come on to the finals. I think these are, again, Mitsubishi. They're the 2904s. Again, we've got a bias tracking diode. We've got, that looks like a thermal switch of some sort. It's just if it overheats, it'll switch on or do something and it'll collapse the RF coming in to, it'll stop this overheating. Or it could be just for the fan. It might have a temperature. Yeah, I think that might even just be for the fan. So there's a fan back here, and that when it gets to a certain temperature, it switches the fan on, so it's not running all the time. And then we've got this here. I'm not quite sure what that is. It says it's a resistor. I haven't looked at the circuit diagram, but it might be thermal couple. It might be something that's, in the ALC, maybe. I don't know. And then we come into another transformer. This is basically a combiner, so we double it's balance coming in, and then it's single, unbalance coming out. And again, that'll be doing some impedance changing. We've also got a transistor here, which is Q4, which I imagine is that's the bias in, it's going to be a stabilizing circuit for the bias. Okay, and if we have a look, and obviously at this point, this is where the RF leaves the board. And if we come over here, let's have a look. Might have to zoom out a sec, just one. And this is our low-pass filter. I mean, it's an array, so basically the microcontroller will switch each relevant relay setting, depending on what frequency we're at, and it'll work it out. Obviously, we need a low-pass filter to get rid of all the other order products. It's actually the harmonic. So there's there'll be a couple of prevalent harmonics coming off this, and that collapses it all. So it's critical it gets the right frequency low-pass filter switched in, and then Bosch, we're out the antenna socket.